Hi everyone, welcome back to Grafana Call 9. In this session, we'll be diving deep into tracing and explore ways to get more insights into your traces using Grafana Tempo. I'm Kunat, and together with my colleagues Ananya, Marty, and Joe, we'll be showing various ways to explore your trace data. In this session, we'll have three sections. So first up, I'll talk about the metric generator, our new component to derive metrics from traces. Next up, we'll be presenting our next generation backend format based around Parquet. And finally, we'll show our work on TraceQL, a query language specifically designed for querying traces. With that said, let's just get started. So first up, the metric generator. So the metrics generator is a new component we added to Tempo 1.4, which can, generate metrics from traces, kind of like as the name says, right? So now when you're storing traces in Tempo, you can also get this derived metadata directly from Tempo, which provides more insight into your traces. And you might be wondering, if you're already storing traces, why should we bother also generating and storing metrics about the same data? Well, metrics and traces each have their own strengths, and combining them really brings out the best in both of them. And being able to combine them in a single UI like Grafana is just a superpower, honestly. So a trace, for instance, is very narrowly focused on a single transaction in your system. You can see exactly how requests flow through your system and what every component did. Traces are highly structured and have a lot of metadata attached, but it is actually kind of difficult to figure out, whether this trace is an outlier or not. Like if you're looking at a handful of traces, was every request this slow? Is this an abnormal amount of errors? You can't really see that, right? Metrics, on the other hand, are aggregated and allow you to see the forest for the trees. They're great at showing historical trends and show patterns in time. So they can really augment traces in this area. With the metric generator, we're bringing both worlds closer together. So the metric generator can generate metrics from traces. And by adding exemplars to these metrics, we can jump back from the metric to a trace that was part of the metric as it was recorded. This is all great. What metrics are we generating? So we have span metrics and we have service graph metrics. Span metrics are red metrics, but based upon trace data. So for every span ingested by Tempo, we capture the rate, the error rate, and the duration of that span. So this way we have an historical count and latency for every span ingested. While this is pretty simple in concept, you can do a lot of very powerful things with this. To give some examples, you might be looking at a trace and wondering, the specific span, how often was this called in like the past hour? Using the rate, you can visualize this, you get a graph in Grafana, and you can see, it goes a bit up and down and maybe changes in time. With span metrics, you can do this for every span. So you can just grab an internal span and also do the same thing and visualize the rate of the specific span. And so this way you can already start investigating like all parts of your system. It doesn't have to be the endpoints. It doesn't have to be manually instrumented using metrics. If you have instrumented your application with trace data, you can get metrics for that component. Besides rate, we also capture the latency of every span. So in this case, I am showing the P90 latency for the specific span, which in this case will be the P90 latency for that request, since it's the root span of this request. As we're generating this metric from traces, we also immediately add exemplars to these metrics. And they're visualizing Grafana as these little squares on top of the time series data. When you hover over them, you get some information about this specific request. You get the exact latency of this request, a bit of the labels, and also a trace ID. Using a trace ID, you can jump back to the trace of that request, and you can see exactly what happened during that request. So this is really a great way to quickly find outliers in your data and see what happened, why this is an outlier, what happened during this request. Span metrics can be broken down by different dimensions. So we, for instance, captured the span status, and this is a visualization showing the amount of successful spans compared to the amount of failed spans. You can also add custom dimensions based upon attributes present in your trace. So if you always have a cluster or namespace attribute, or maybe you have a customer ID, These attributes can be picked up and added as labels to the Prometheus metrics. The second type of metrics we're generating are service graph metrics. Service graph metrics extract service topology out of trace data and visualize it in a node graph. Let me just show you how it works, right? So if you look at this trace, you can see there are a couple of services involved with this request. You can see this by looking at the different service names in the left column or just looking at the colors. In this case, the request starts in the gateway, which does some work, and then forwards the request to the distributor. So you can see that's the first jump. And then the distributor will send 3 requests to the ingesters. So that's, again, 3 jumps. With the service graph processor, we can extract this information out of the trace data, detect the jumps, and keep track of the rate and latency for every jump between 2 services. If you do this for all the traces that are being ingested by Tempo, you can draw this service graph consisting of all the services present in your system. Not only can you see all the services, you can see how they're connected with each other, which service calls which other service, how often do these requests happen, and what is the average latency. We show some data on this node graph. For instance, if a service is struggling and a lot of requests are failing, this will show up as a red segment on the ring. And if you hover over a node, you can also see specific data about the connections between services. So you can see the exact amount of requests between them. If you click on a node, there's a context menu allowing you to open the underlying metrics. So in this case, this is the metrics for all the requests sent to the ingester service. And this service receives requests from 3 different clients. So we have latency for every connection between them. Just as with the spam metrics, we also collect exemplars for this. So you can also explore specific requests. Spam metrics and service graph metrics are based around the same trace data, and we can combine them together in one view to give you an holistic view across your system. So service graph metrics can give you a good overview of your services, show you how they're connected with each other. You can see how many requests are sent between them. And we can use spam metrics to show you the slowest requests within your system. So we can use spam metrics to show the slowest spans, how often they are called, what their average latency is, and how often they fail. Combining them, you can really quickly figure out, which service is struggling right now, which endpoint is the slowest, or which endpoint is failing all the time. I'm going to wrap up here because, I can talk hours about the metric generator. So as the last point, how can you use a metric generator? It's available in Grafana Tempo 1.4, which was released last month. It's an optional feature, so you have to enable it manually. And we also run the metric generator in Grafana Cloud Traces. So this is an opt-in feature. Reach out to support to enable it. And then we can generate metrics for your tenant and automatically send them to your hosted Prometheus instance. With that said, I'm going to make room for Ananya and Marty.
Thanks, Kunrad. Hi, everyone. I'm Ananya Agarwal, and I'm a software developer here at Grafana Labs. And today, I'd like to talk to you about how we're using Apache Parquet to bring blazing fast search to Tempo. Before I get started, I'd like to quickly recap the history of implementing search in Tempo. So we launched Tempo in October 2020. Back then, it was a key value store with a strong integration with Loki and Prometheus to enable trace discovery. In June 2021, we launched Tempo 1.0, and this marked the key value storage stable and the cloud-hosted traces as generally available. And this was a milestone because beyond this, the team really started focusing on implementing the next key feature around searching over trace data. In November 2021, we launched search over recent data that we store on ingesters. And to do this, we used a complementary flat buffer-based search index along with the proto data on the side. Soon after, in Jan 2022, we launched full backend search using serverless technologies. And this would launch cloud functions to search over protobuf data present on the object store backend. But as we implemented full backend search, we realized that we needed to fundamentally change something like the backend format to enable queries over large data sets and unlock queries over more than 24 hours and also unlock TraceQL. And so this is why we started really investing into Parquet as the new storage format of choice. So what is Parquet? Well, Parquet is an open standard under the Apache Foundation. And to quote from their website, Apache Parquet is an open source column-oriented data file format designed for efficient data storage and retrieval. So what does this mean for Tempo? For Tempo, it means that we can store and access trace data more efficiently. And we'll talk about this in the following slides. It also means that as an operator, it unlocks a whole ecosystem of tools that work on Parquet files on object storage. So these tools could be Presto, Spark and Flink jobs, and a host of other tools. And the advantage is that these tools also unlock new query languages like SQL. And these are so popular across the industry that it opens doors for a lot of folks to write SQL queries on top of trace data without having to touch the query part of Tempo. And since Tempo is already highly optimized to work with files on object storage, it does heavy parallelization to efficiently search over files in the object storage. Parquet fit right into Tempo because it's just a new file format and we didn't have to set up any new infrastructure to work with Parquet. So now let's look at what storing traces in Parquet actually looks like. So a trace typically looks something like this, right? It's got a trace ID, it's got a start and end time, it's got a couple of spans, and each of these spans has a name, a service name, a couple of tag attributes. Each of the spans has a start and end time, and possibly an event like a log line attached to it. So I'm just going to take these schema attributes and lay them out in a different manner to make it intuitive to work with Parquet files for this presentation. And I'm going to colorize them to make them a bit more fun. So finally, we can see that this is what a block of traces looks like. Each of these rows is a trace and a column is an attribute over all of the traces. And we're going to assume for this presentation that this Parquet data file is a gigabyte long. And since Parquet is a columnar file format, of course, the on-disk layout is going to look something like this. So all of the trace IDs for all traces are going to be laid out in a contiguous block, followed by a contiguous block of duration, span IDs, and so on. But for this presentation, we're going to assume a layout like this. And we're going to see 4 key features that Apache Parquet is going to unlock for us to make searching very efficient. The first is around encodings. What Apache Parquet allows us to do is to choose a unique compression encoding for each column depending on the column type. So if we have a duration column, which is mostly integers, we could use the delta encoding, which works really efficiently on those. And if we have a tags column, which has mostly strings, we could use the dictionary encoding that works really well. And finally, if we have an events column that we're not going to support for search, we can use the snappy encoding to just compress all of that data and dump it into the block. Next, let's see how find trace by ID works on the Parquet file. So when Tempo is queried for a trace ID, we're going to scan through the trace ID column, as you would have already guessed. And this trace ID column is 2 orders of magnitude smaller than the size of the entire Parquet data file. It's just 10 MB where the Parquet data file was a gigabyte long. And so this is really efficient. And when we find matches, we can just skip over the rows before the matching row and just read the row that we're interested in. This also helps to reduce IO further. And finally, when we want to display the trace, we can convert it into protobuf and render it on the Grafana UI. Now let's look at a more interesting query around attributes. So this is typically the use case where the user comes in and queries for a cluster and a namespace and some other selectors. And all of these are part of the span tags or the resource tags that are part of the trace. So what we're going to do here is actually scan through the tags column. And this is, again, an order of magnitude smaller than the size of the entire data file. So it's much more efficient. Also, if you remember, we use the dictionary encoding on the tags column. So if a user queries for a term that's not present on the tags column, then it can just skip through it because it's going to look up in the dictionary. And if it doesn't find it, it can just skip the entire tags column. But in the case that the key is actually present in the column, it's going to find those matches. We're going to read those rows and render them in the table that you see in the Grafana UI today. Finally, and this is a really exciting feature, is that Parquet has a flexible schema. So what we can do is actually introduce new columns without altering the query patterns for the existing columns in the file. So the way we use this today is to have an opinionated list of columns that we think are most commonly used. So for example, cluster, namespace, HTTP URL, and all of these columns we believe are highly common. We're going to pull these out of the tags column and blow them out into their own columns. So that when we get a query for one of these columns, like cluster foo and HTTP URL grafana.com, all we need to do is actually scan through these columns, which is another order of magnitude smaller than the tags column. So this further helps to improve efficiency by reducing I/O. We also have on our roadmap a plan to implement dynamic schemas where each unique tag would be blown out into their own column. We have a proof of concept working in our local environments, but it's early days and we want to experiment further before we productionize it. So now let's look at what a block with Parquet data files actually looks like. So Tempo is going to write the data Parquet files, as we've seen in the previous slides, into a block and store it in an object store. So the hierarchy of the object store bucket looks something like this. So we have the bucket ID, and then we have the block IDs, and under that we have a couple of files that involves metadatas, Bloom filters, and then the data Parquet. Since Parquet is an open file format, we can use a host of existing tools to actually unpack the Parquet file, read its contents, including the rows, check what the size of each column is, see the number of rows that are present, and a lot of other functionality. These are really powerful tools. Versus what we have as of now is a custom file format where we have a data file consisting of compressed protocol buffers of the traces appended to each, appended one after the other. And we have an index file that contains location of pages in the data file. So we have a CLI command that actually helps to scan through this data and index file. But again, it's not an open file format like Parquet. So that brings me to the end of this presentation around Parquet. All of what we discussed in these slides is part of this design proposal that's open on the Tempo repository. Please do interact with this PR. Suggestions, feedback, comments are all welcome, and we look forward to hearing from you. So now I'm going to pass it over to Joe to talk about TraceQL. Thank you.
Thanks, Nanya. A bunch of great stuff about Parquet coming up. Really excited about this new backend format. I really think it's going to be the next evolution of Tempo, the next steps. While we're talking about next steps, though, let's get into TraceQL. So TraceQL is the upcoming query language for traces that we've been talking about. There's been a handful of PRs to the repo, and if you're participating in our Slack, you've seen a lot of this already. But let's get into some of these details. So we're going to talk about selecting traces. TraceQL, as it's written now, the various proposals and the parser that's already been PR'd to the repo are really focused on trace selection. So basics. What is the most basic thing you're looking to get out of selecting or finding, searching for traces? Basic things are just going to be span attributes, their names. Duration is, of course, very important, a very common thing to look for. Status, does it have the status code set to error? Also all the custom attributes. There's custom attributes both on the span and at the resource level. All of this, of course, needs to be searchable in your tracing backend. So here's some basic queries that are just going to search for some of these properties of the span. You can see we have this idea of intrinsic attributes like the duration or the name. These belong to every span. You can't not have a duration. You can't not have a name. They are always there. And then we also have, of course, the custom attributes. So at the top, we see some of the intrinsics and some of those options. And on the bottom left of your screen, you should be able to see, the various attributes. So a custom attribute like HTTP status. Notice that you can use the dot to proceed to mean both span and resource, or you can specifically prefix and say, I'm looking for a span, or I'm specifically looking for a resource attribute. All of this is available. There's a lot of common operators here. Nothing surprising, I don't think. Just looking down the slide, we have greater than, less than. There's a regex operator for strings. We have the ability to do and various conditions. So that very bottom query right there is important because it's going to assert both of these conditions, HTTP URL endpoint and HTTP status 200 on the same span. So both of these things would have to be true on the same span for the trace to match, for the span to match, and therefore for the trace to match. So basic ideas is kind of what you'd expect. We just want to select on the basic properties of a span, very quick and easy, jump in, search for a trace. Next, aggregates. So a lot of times you need a little bit more power than that. You don't necessarily want to select attributes of a single span, but let me ask a question about a collection of spans within my trace. I'm going to aggregate a set of spans, and then I can add some kind of conditions and filters based on that. So here's two common aggregates that we're planning on building. The first one at the top is a simple count. So it is first applying this filter, DB systems Postgres. We're looking for database spans, some spans related to a database call. I'm then piping it to a function count, which is going to count the number of spans that match that condition. And if it's greater than 3, then I return this particular trace. Maybe I am suspicious that certain number of database calls in certain traces is actually causing some problem. And I really want to select those very quickly. And I'm looking to find the traces where I have a certain amount of database action. I want to go hone in on those. This is a great query to pull that off. And the second one is a different kind of aggregate. So in this case, I'm looking for spans that match name, DNS lookup, and then I'm taking their average duration. And I want to only look at those traces where the average duration is over 500 milliseconds. So I have this suspicion, I have this theory. My slower queries are because my slower queries are caused by a slow DNS lookup. Most of my DNS is fine, but every once in a while I have a really slow lookup and it makes a slow query. Let me go find some of those. Let me go see how many of those I have. So the second one is averaging a property of the spans, the duration, and then I'm comparing it to the 500 milliseconds. These aggregates also expose a very important property of the TraceQL language, something I think is very important to understand about the language that gives it a lot of its power, which is that this query you write is a pipeline of span sets. So that we start over here on the left with the whole trace. At the very beginning of the query, the entire trace is considered the span set. We can then move it through some pipes or some piped operators, and each operator is going to reduce the span set until the trace either survives the query or is completely filtered out by the query. So that first part before the pipe is going to only find the spans where name is DNS lookup, that's 2. And then past this, we're going to go to the next operator, and we're going to see if the max duration of those 2 is greater than 10 milliseconds. And it is. So these 2 spans are returned, and this trace is returned as a result. Here's a second query, name DNS lookup count greater than 3. The first filter found 2 spans, and it reduced the span set of the whole trace to 2. The second filter doesn't pass because count greater than 3, it's counting the number of spans remaining in my span set, which is only 2. It doesn't pass, and this trace is dropped. So thinking of the query as a pipeline of spans is important. And I think it's really powerful because if we return a set of spans, our results set can include sets of spans. So when I see my results in a UI, I'm picturing, I'm seeing a trace, but I'm also seeing the 3 or 4 spans that matched my query. And maybe I can deep link into that trace. And I'm going to immediately get some deep insight into how this particular trace matched my query. One of the final properties that we really were thinking about when we made TraceQL was the structural nature of a trace. So a trace is often thought of as a tree structure, and for the most part it is. It's not entirely true. You can actually have links cross spans, but that's rare. So 99% of the time, a span isn't a tree structure, and the primary relationship in a span is a tree structure, where every span has a parent except for the root, which has no parents. So we were looking to get into this basically. We are looking to take advantage of the tree structure and make the tree structure an important element of TraceQL. So at the top, I have a query that we're using using an operator we call the descendant operator. So this particular operator is going to first find all of the span sets where a service name is foo. And then it's going to find all of the spans where service name is bar, and it's going to take those 2 sets of spans, and the operator, the descendant operator, is only going to return a span set if one is a descendant of the other. So in this case, I'm basically looking for a query, or sorry, I'm looking for a trace that started in a service foo and ended up in a service bar. I can like assert something about the structure of the tree, how the trace passed through my services, how the trace passed through my environments, regions, whatever is important. That second query there with the tilde, that we're calling that the sibling operator. So this is looking for two spans that have the same parent, basically. So find all the spans where the name is TCP connect, find all the spans where DNS is lookup, and then only return those spans that have that sibling relationship between the two. And a final structural element of the language is this parent service name, or sorry, the parent kind of scope on an attribute. So service name does not equal parent service name is going to match any spans that cross a service boundary. So my service name, this span right here, is not the same as my parents. If I can reduce my span set to that, I'm only going to get basically the root span from every service in my trace. Cool. So structural queries are important to us. This idea of the pipeline of span sets, we have aggregates, we have the basic matching. Where are we headed next with all of this? I think the next steps for Tempo, or sorry, for TraceQL is definitely metrics. So of course you have LogQL, you have metrics. Prometheus is all about metrics, right? And Mimir. But Tempo does not have a way to select metrics yet. And that would be kind of the next thing we're looking at. So take one of those pipeline span sets. Let's attach another operator to that lets us count the rate at which we see a span, or do a histogram of the duration, a live histogram of the duration of a set of spans that match some conditions. So after we kind of start tackling this core set of functionality, what's coming up next is this idea of metrics from your traces and from your spans. I'd like to thank everyone for joining us, as well as all my co-presenters. I think Kunrad kicked us off. Then Ananya gave us some great information about Parquet, finally, the TraceQL part. And then I think Marty is also joining us for the Q&A in a second here. So we'd be glad to answer any questions you have. Also, thank you so much for joining.